All right, so we are faced with this example. A 900-gram stone, a 900-gram stone. Let me just draw it anyhow. Of course, I'm not good at drawing. Let me just draw it anyhow. Okay, this is 900 grams. Okay, is pushed along a tarmac. Okay, by a horizontal force of 20 newtons. Okay, a frictional force of 12 newtons opposes the motion. Now, opposes the motion means it's moving in a different direction. So as you all know that friction opposes motion. So that means the frictional force is going to be moving backwards because it's opposite to the horizontal force rather. So the backward force is actually 12 newtons. 12 newtons. Okay, now the question is, what is the acceleration? Now we have the mass to be 900 grams, yes. But then we have to convert it to kilogram, and that'll be 900 divided by 1000. And that gives us 0.9 kg. And then we have our force. So that means if this force is 20 newtons and this is 12 newtons, this one is going back. So what's the resultant force? The resultant force is actually, the net force is actually going to be 20 newtons minus 12 newtons. And that's going to give us 8 newtons. Why do I have to subtract that? Because this is actually moving in this direction and this is in this direction. So it's opposite. So I have to subtract them from each other. Okay, so the net force is actually 8 newton, and it is since it's positive 8, then that means it is moving in the right direction. Okay, good. And we know that F equals to what? MA. Okay, from that, the force here is actually 8 newton equals to the mass 0.9 A. Then that means I have to divide both sides by 0.9. Divide both sides by 0.9. Okay, then this cuts this out, then I'm left with A is equal to what? 8 divided by 0.9. What I have is 8.89 meters per second squared. Never forget your unit. Now, one other thing that you have to note is that in JAMB post-UTME, what they do is that they test for speed and accuracy. So that means that you would have to know your units of each physical quantities or derived all of your physical quantities. Now, so sometimes they can give you option 8.89 meters per second A, then B 8.89 meters per second squared. What is the acceleration? So you should be able to differentiate between 8.89 meters per second and 8.89 meters per second squared. Meters per second is velocity or speed, and meters per second squared is acceleration. All right, so good. Then let's move to the next example. So there we go. We have a ball of 0.7 kg moving, a ball of 0.7 kg moving with a velocity of 50 meters per second. It suddenly hits by a force of n newtons from the back, 6 newtons from the back, okay, with a time of impact 0.03 second. Find its new velocity. Now there's a change, so that means this guy here, this ball will now be moving in a new speed. Don't know what that is, so that's what we have to find. So that means this is going to be u, and this is v. So now the change, remember that impulse is equal to change in momentum, that's ft equals to mv minus u. We've talked about that before, and this is, all of this here is impulse, because force times time is actually impulse. So you have 6 multiplied by 0.03 equals 0.7, then open your bracket, v minus 50. So if you open up that bracket, 6 times 0.03, what you get is actually 1.8. So you get 1.8 equals, open up the bracket, you have 0.7v, then minus 50 times 0.7, what you get is minus 35. Okay, then what you get is 1.8 equals, 1.8, I'm going to bring this down here, and that becomes positive 35 equals 0.7v. And 1.8 plus 35 is actually 36.8 equals 0.7v. And if I divide both sides by 0.7v, divide both sides by 0.7v, sorry, 0.7 rather. So what I get is, this cancels out this, and so I'm left with v becomes 36.8 divided by 0.7, and that becomes 52.57 meters per second. So this is the final velocity. This is the new velocity at which the ball is moving. Remember that the ball was moving initially at 50 meters per second. Now, because there's an additional force, it now moves more faster. Then it moves at 52.57 meters per second. So you can see that this impulse here has added more momentum to that body. All right, good.